Hey yo, what's up, YouTube? It's your boy JOHHABRAHAM. We're back with the intro to general chemistry. We back, son. Even though it's pretty late, we're back, son. What did I just close? I should not be closing that. Let's follow let's follow the timetable. Quoted. Damn. I don't have enough money to buy coffee, that's the problem. So what was that thing? Yeah. Okay, take this, take this. Take it. Gotta do one more thing. Yeah. That's plugged in. Intro to general chem. 1 hour, right? Hey Siri, set a time for 30 minutes. Periodic table. I need to write the periodic table, like the basic information related to periodic table. I still haven't written those. Also, periodic table. Shut the I just checked the YouTube stream to change the description. There's a fucking advertisement. Ain't nobody give two shit about advertisement. Okay. It was a mess. Why are all these things here? Let's fucking go. So, periodic table of elements. The cell number is calculated from atomic number in correct weight if you want to know what the outer shell do. I did write the short summary of what are okay. So let me get this straight. So small electrons, small or electron which higher nuclear pull due to higher number of protons. So now if we consider this as a wave of electrons, are the nuclear pull as a sort of positive wave that balances the negative wave of electrons. In case of smaller non-nuclear pull atoms, they have higher positive wave that has more strength to balance another electron if it's given compared to electron affinity. Okay, now I just read about the periodic table yesterday, and I'll just write up all the things that came to my mind and just let me know if that basically summarizes the periodic table. So the more modern periodic table is arranged based on the orbital. Modern periodic table is arranged based on the orbital. The valence electrons are filled in like the s block consisting of columns of 1 to 2, and outer orbital is s orbital. Outer shell in which the valence electrons exist is the s orbital, like that from 3 to 12. Come on, 23 3 to 12, it's d orbital. From 12 to 18, it's p block. And the second last and last row of the third column, there's two new rows separated consisting of 14 columns. Uh-huh. Uh, 4, 14, yeah. 14 columns. These elements have valence electron filled in the f orbital. Hence f block. These are one set of these are one set of separation in the periodic table within the second element which form with the second element which from what I said would belong to the p orbital, but second element would be a part of s orbital. Then the atomic radius increases from top to bottom as part of the increase in principal quantum number, which results in increase in atomic size. Then atomic radius increases from left to right due to the increase in intranuclear force due to the increased number of protons which pull the electron, reducing size. Ionization energy is the energy required to remove an electron, especially valence electrons, from its outermost orbital, and from top to bottom this ionization energy decreases as increased atomic radius helps in easier ejection of electron, while IE is opposite for left to right. The ionization energy required will increase as smaller atomic radius means more intranuclear effect for the electron to be ejected. Electron affinity is the energy required to add an electron to the outermost orbital where the valence electrons exist, and this strength from top to bottom electron affinity this trend from top to bottom. Oh, okay. I think only the electron affinity was 1 to 2, 3 to 12, 13 to 18. 1 to 2, 3 to 12, 13 to 18. Let me try writing this. From top to bottom, atomic radius increases. Left to right, atomic radius increases. Ionization energy decreases from top to bottom. Across the period increases. Wait. Left to right, atomic radius decreases. Wait. How? It's increasing, right? So more electrons. Smaller atoms, stronger attraction. Okay. From left to right, atomic radius decreases. Therefore, ionization energy increases. What else? Electron affinity, that's the opposite of ionization energy, so it's gonna be down the group. Electron affinity increases and across the period decreases, right? Periodic table of elements. Bam, 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 bam. You know what? Let me just write it one time before on the screen. Okay. That sentence was not right. Let me write it one time, not shared on the screen, like on my own. S block. Now 3 to 12. D block. 13 to 18. P block. God damn it. The last two. How long is the F block? Oh, it's all the way. Okay. Five to 14 or 4 to 18. Okay. Mm-mm. 5 to 18 or 4 to 17. Mm-hmm. These are mm, valence electrons are filled in. F block. That's F block. Now, what else? Atomic radius. Down the group. Increases. Atomic radius. decreases. Why this atomic radius decreases from left to right? I need to so from left to right. But it's filled in. Mm. Atomic radius does not increase from left to right, it decreases. The reason is very straightforward. Nuclear charge increases. Okay, more protons. Okay, I forgot about the protons. Okay, okay. Got them. The same. The same logic. Protons still apply for top to bottom. More atomic number, more protons. But the effect of the atomic radius is different because something much bigger happens when you go down to a group. Proton number increases tend to pull electrons inwards, would normally shrink the atom. New shell is added. Okay. Okay. More shells, resulting in electron shielding effect. More protons to pull in electrons. Mm-hmm. So now it's ionization energy. That's the energy required to eject an electron from the outer shell. And ionization energy decreases from left to right. Ionization energy increases. It's the opposite. Ionization increases from left to right as smaller atomic radius, harder, smaller atoms, harder to eject electrons. So now it's ionization energy, electron affinity. It's the energy required to add an electron to. So electron affinity, there's a lot of exceptions, but there's going to be a lot of exceptions, but electron affinity usually uh, is lower for smaller radius and higher for bigger radius, because smaller radius proton has more attractive proton, or the nucleus has more attractive effect and could pull in the external electron faster. While larger radius, it's the opposite effect. Nucleus has less effect. Outer electron, so more energy, more external energy is required. So that's electron affinity. Now what we got? Electronegativity. No, that's for the entire general chemistry. The structure of periodic table. Ionization energy. Oh, I forgot electronegativity. Negativity increases from left to right. Across a period, adding an electron is favorable. Smaller, yeah, yeah. Okay. Electronegativity, ability of an atom in a bond to pull shared electrons towards it. Trend, uh, left to right, smaller electrons increases. Okay. So Electronegativity, ability to pull electrons, which is also a similar trait compared to electron affinity. Or so En increases from left to right, En decreases from top to bottom. What the oh, what the no. Effective nuclear charge. A Z effective, positive charge by valence electrons, actual protons. But shielding stays near the same outcome. Nucleus pull electrons more strongly. So electronegativity and effective nuclear charge is same, almost same. Wait. So electronegativity and the nuclear charge. Wait. Effective nuclear charge. They're related but not the same. Effect. How strong a nucleus pull an electron, especially valence electrons. How strongly an atom will share electrons when forming a bond. So electronegativity is how much the atom has the ability to pull in electrons. This usually matters when it's in a bond, like when it's sharing electrons with the other atoms. Well, effective nuclear charge. Effective nuclear charge is also the same as uh, electron affinity, but almost looks the same as electron affinity, but this one is for outer. This one just represents the relation between the nucleus and the valence electrons. That's basically it. Okay, if I start writing, let's see if I could write it. So now we're gonna talk about the periodic table of elements. That's the next part. And the periodic table looks something like this with one, two, row 1 and 2 with the S block. And then from 2 to 12 is gonna be, oh shit, there's no back button. 2 to 12, 3 to 12, it's gonna be D block. And from 13 to 18, P block. With an exception of the first element in the P block being S block, but it's 13 to 18. Oh, there's one more. At the second last and last two parts of the D block is extended to form the F block. It's from 3 to 17. I'm a bit confused, but that's F block. So now let's talk about, let's make it 2 columns, and this side represent from left to the right of a periodic table, and this side represents top to bottom. And the first trend would be for atomic radius. Atomic radius decreases from left to right as when we go from left to right, the atomic number increases, but not the shell number or number of shells. So there's going to be more protons on the same atom the more right we go. There's therefore more electron pull. Like the nucleus is going to pull the outermost electron, resulting in smaller atomic radius. And the opposite is going to be for top to bottom, where we do have increasing atomic number resulting in more protons, but another thing is we have more, how do you say, energy levels, so there's going to be shielding effect. So yeah, that's why from top to bottom atomic radius usually decreases, and this is just a standard form. There are exceptions. The modern periodic table is still not the best. It's the best we have, but it's not perfect. Now what atomic radius, electron affinity, ionization energy. Ionization energy, it's the energy required to eject an electron from the outermost shell. And that would be first order ionization energy. The more electrons we eject, that will be second order, third order. It just goes further. So ionization energy, that is gonna, from left to right, ionization energy is gonna increase due to smaller atoms, small smaller radius, smaller radius, more energy required to eject. Now for from top to bottom, that's the opposite case, because ionization energy decreases, less energy is required due to less nuclear pull, or less pull from the nucleus. That's what, so bigger the atom, bigger the atom, less IE. Now what's the next concept would be electron affinity. Energy required, that's the energy required to add an electron into the atom. So that's going to show the opposite reaction compared to ionization energy. For example, electron affinity is lower for smaller atoms because less energy required to add atom, because high nuclear pull due to small size. Smaller atoms have higher nuclear pull from the center or from the protons, so it's easier to add an electron, if you know what I mean, But in the case of bigger electrons, electron affinity increases. More energy required to add electron due to less interaction from the nucleus as the atomic radius is big. The shielding effect, all these are what contributes to the higher electron affinity. Now, what was it? Electron affinity. What's next? Electronegativity. Electronegativity, that's the tendency, you could say, tendency of the atom to pull in an electron. It's similar to electron affinity, but yeah, just like that, electronegativity, let's write En, is lower for smaller atoms as more protons pull more electrons, or has the tendency to pull more electrons, while in the case of larger atoms or larger radiused atoms, electronegativity increases. Sorry. Electronegativity increases for smaller atoms as it wants to pull in, and electronegativity is lower for bigger atoms. Large size results in less tendency to pull. Forgive my vocabulary, I'm still learning, okay? Less tendency to pull in external electrons. Now I'm gonna be writing the last one, or almost the last. It's called effective nuclear charge. It's a Z effective. That's what the symbol is for. Symbol is usually referred as Z effective. What was Z effective? Effective nuclear charge. That's the let me just cross check, okay? Yep. So effective nuclear charge is you could say it's almost similar. It's the interaction between the nucleus and the valence electron. Valence electron, outermost most electron. So Z effective is higher for smaller atoms, as due to their smaller size, the nucleus has more effect on the external electrons. Due to small size, the nucleus attracts the outermost electron. Now, effective nuclear charge for bigger atoms is going to be low, because due to the large radius, shielding effect, etc. Less attraction between the nucleus and the outermost shell. No, that's not correct. Outermost shell. Now that would be, these are just common trends. There are still a lot of exceptions for these, especially when it comes to electron affinity and F block. Lot of exceptions with F block. So there's a lot of exceptions, but this is most of the trends that are seen in the periodic table. Effective nuclear charge, electronegativity, electron affinity, ionization energy, atomic radius. And yeah, this is basically what the periodic table looks like. And I don't know if I did not mention, but the S block, D block, P block, F block, these for percent, the valence electrons shell. Yeah, this represents where the valence electrons are situated. Especially for these two, it's going to be S block, D block, P block. That means 2 electrons, 6 electrons, 10 electrons, 14 fucking electrons. Hell yeah. Well, I think that's basically it for periodic table. Peace! I guess, but I'm still confused. There should be something between atomic radius and electronegativity. I feel like I missed something. What was it? What was it? I guess, yeah, ionization energy, that's what it said. Well, then, I guess that's periodic table, right? I can just skip periodic table now. Chemical bond. Oh, it's 120. You know what? I'll start with question paper now. That's what I planned. 1 hour question paper, 1 hour of theory. Where's the questions? Let's go for this one first. Oh, did I just do that? I'm sorry. Okay, so delivered. Where did you deliver this? It's downstairs. God damn it. Okay, okay, okay. Think, think, think. Before I do something, I have to send a message to two people. I have an exam next week. next one would be the student union. Come on. I apologize for wasting time, but we gotta do. Okay, that's out of the way. Twitch and YouTube, I'm just gonna mute for a while, just a minute. I just need to check one thing, and I don't wanna disturb with the audio. Okay, I was just checking one thing and we're back. There's more book. Now write down the 5 steps necessary to formulate a correct redox reaction in an aqueous solution. That question I seen more than once. It's 5 steps to balance split the reaction into two half reactions. Balance all atoms except O and H. Balance oxygen using water and hydrogen using H plus. Balance the charge using electrons. Equalize electrons and add the half reaction. Hmm. Hmm. What is this? We're pleased to announce Beat the City. All participants will receive a 40 exclusive 40% discount on what? It's identify the oxidation half reaction, reduction half reaction. Balance all atoms except O and H. Mm-hmm. Just a minute. Oh, there we go. Pie chart's still there. What? Oh no, that's too big. Periodic table of friends and elements. I think that's valid. I do think that's valid. Boom, 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 boom. Oh shit. be right back. Mm, mm. Beep, 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 beep. I don't think I put that part. Let me just cross check just a minute. Just a minute, just a minute, just a minute. Nope. That's out of the way. White Charm, I think you should go to sleep. Go sleep, brother. That was the worst. Ba 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 ba. I really do need a coffee, not gonna lie. I would like a coffee, but oh boy, coffee's not looking good, I guess. Split the reaction into two half reactions. Identify. You know what? Yo, what the fuck? Where are the headphones at? What? I got the headphones and I'm just gonna go downstairs to get my tubes. Like I ordered two rubber tubes for my bike. I would want to go get that because I don't want, it's a dorm. Got him. Oh, if this thing is fucking crazy, I can't. That's it. That's two tubes. Okay, that's two. That's basically it. That should be it. Now. Focus! Hocus pocus, focus! Magnesium. Magnesium. Quadroxide? What? What's O4? Plus Fe2, Fe2 plus gives Mn2 plus Fe3 plus. You know what? I'm gonna put that there. Fe3 plus split into half reactions. Oxidation, electron loss, Fe2 plus, Fe3 plus, reduction, electron gain. So iron is gonna lose electron, magnesium oxide is gonna gain electron and move oxygen out of the place. Devoto did. Hi Josh. Hey yo, I appreciate Devoto did for checking out the stream. What was I thinking? Yeah, step 2, split into half reactions. Step 2, balance all the atoms except OH. Fe is already balanced. So Mn is already balanced. Reduction half still has oxygen to fix. Balance oxygen with H2O. Can we get an example? Oh, so weird. Oh. Can we get an example that makes use of the wait? Like here, the step 2 was not used at all. Was not the Fe and where's the mouse? Some sort of glitch. Sure, let's go. Where is this, bro? Unbalanced equation, magnesium hydroxide plus C2O4, 2 minus, okay. Now let's balance, separate into half reaction. C2O4 converts to CO2, so that's oxidation. Reduction. Magnesium undergoes reduction. Balance the atoms. To Mn is already balanced. Okay. Uh, Balance oxygen using H2O. So H2O goes to the other side. Got it. Got him. Balance charge using electrons. Uh, Wait. So we got 5-2. God damn. So we have to add them together. That's the answer for first question. How many questions do we got? 14. Fourteen, 14 plus 13, 27. 41. 41 questions. Okay. And right now I'm at first question. Separate into half reactions. Balance all atoms except hydrogen and oxygen. Balance oxygen using water. Balance hydrogen using H plus. Balance charge using electrons. 2 minus. Okay. Ow. We are at 699. We're reaching 700 video. Tough. That's crazy. Remember, separate into half reactions, balance all the atoms. Separate into half reactions, balance all atoms except hydrogen and oxygen. Then balance hydrogen with H2O. Balance oxygen with H2O. Step 4, balance hydrogen with H plus. Balance the electrons. Charges. Balance the charges using electrons. Equalize electrons and combine. Equalize? 5 steps necessary to formulate a correct redox. Now, also, in the question, it's also said that the redox reaction in exactly. Here's why we included. Oh, so so the solution is basically the step uh, Okay, so step one, separate the oxidation half and reduction half reactions. Step two, what was step two? Separate the reaction. What was step two? Think. Think. I forgot. What? Balance all atoms. Oh, yeah. Balance charge using electrons, equalize electrons, and combine. Can we get something that kinda sounds related, like balance the electrons or something? That's step 6. I mean, I could write my answer right. I don't have to balance the electron transfer and combine the half reactions. Okay. So if I'm writing this on my own, how does it look? No. What are these music, bro? Kowalski. Kowalski. Oh, that makes sense. uh, Keep the phone away. Stay away, son. Stay away. Okay, let me write it. 5 steps to formulate correct redox reaction in aqueous solution. So, 5 step to redox. Step 1, separate the oxidation half-life and reduction what was the equation we got? It was let's write it here. MnO4 minus plus C2O42 minus gives Mn2 plus CO2. So magnesium C2O4 lost electrons. So loss of electrons. Okay. What's up? So how will I decide if which part goes which of the which part goes to which of oxidation and reduction half reaction? Is it just the compound losing after the reaction will be oxidation half reaction and the one gaining electron after the reaction would be the reduction half-life. Exactly the general rule. Species loses electron, species gain. Okay. Loss of electron, gain of electron. Now, how do we realize if we lose or gain electron? So, let's take MnO4. So, MnO4 is minus. And now it's 2 plus. What does that mean? Minus means it has one electron extra. Right? I'm just writing this, it's not real. So let's say CO2 plus. That means the CO2 has lost one electron, and CO2 minus, that means CO2 gained 2 electrons. CO2, just CO2 means there's no extra electrons gained or lost. That's okay. So minus 2 plus, that means it lost electron. Loss of electron, oxidation. MnO4 minus gives Mn2 plus. Now, C2O4 2 minus 2 CO2. Now what is this? Wait. 2 minus. So Mn2 plus. It lost 3 electrons. CO4. What? Okay. We're getting more and more doubts. But here looks like both Mn and Co are losing electrons. Let's carefully go through this one. You're right. At first glance, it can be confusing, but track the oxidation. Wait, MnO4 is +7. Oh, I don't know if it's +7 or not. I mean, oxygen has -2, right? Wait, oxygen has. Uh, Wait, I forgot. How did you know that the Mn? Anyway, no, none of these. No, no, no. I didn't see anywhere in the equation mentioning that. These comes after. Ow! Oh, my eyes. Ow! Ow! Wait. Wait, so I can't do this. Redux. So, 5 into 27. 125, 125 plus. There's a set of rules aligning. Mother halogens. uh, think I have a lot of questions. Uh, the first question that comes to my mind is, how do you know if it's a metal or not? Especially when hydrogen, when it's attached to non-metals, it's +1. Attached to metals, it's -1. I mean, I know a lot of metals. Iron. What's another metal? God damn it, iron. Dude, there should be more metals. Iron, sodium. Sodium's a metal, right? It's a soft metal. So for this example, MnO4 minus to Mn2 plus. So it's wait, where is the goddamn back button? Can I change what's shown here? Customize, yeah. Drag or remove items. There's no back button. Button. That's the most stupidest thing. There is no back button. Let me. You know what, gang? I should cook something, right? Yeah, I should cook something because it's 3. I gotta eat. So, peace out, YouTube. We'll be back after my food. If I'm focused, I'm gonna be back on time. Peace.